Right. So let's go through the rest of the homework. Well, I get unless are there questions before we begin actually? So I released the videos for that where I solve like the whole exam. So yeah, you can look at that if you have questions on the exam. Or we can always talk about it. But all right. So no one wants to ask anything. Let's continue, I guess, with number 5. And most likely today's going to be rather short just because we only have 3 problems to go through. Okay, so number 5, we have a person, height is 2 meters. They're walking away from a street light, which is 8 meters. And we want to find the person's shadow, the length of their shadow. So I definitely want to start by drawing a picture. Okay, so let's say that this is the sorry, the street light, and that this is the person, height of 2, and there's going to be a shadow that's cast. It's going to hit the ground. Okay, and we know something about how fast the person is moving away from the street light, and we also know we want to figure out something about the speed at which their shadow is changing. So because this shadow length is important, it would make sense to label the side that corresponds to that, which is right there. For some reason, my computer's being a bit funny. No, everything's plugged. Okay, yeah. So the side length here, and the person's velocity is also it also shows up. So I'll give that a name. I called it D on here, but I guess I can call it X here instead. Okay, so we know then that X prime is a half meters per second. That's what the problem tells us. And we want to find the rate that the shadow is increasing. So we want to find the yeah, S prime. Okay. So when you see a picture like this, you should immediately think of similar triangles. You've got this small triangle here, and then you've got this big triangle there. And so what we want to do is we want to set up a proportion that relates these things to each other. So the proportion that comes to mind is s over 2 is equal to x plus s over 8. So does everyone see how I got that? Does anyone not see how I got that? Is anybody awake? So it's
I'm
just
awake.
okay. That's good. Okay, finally, yes, I got a thumbs up. Okay, good. So I mean, I can't tell, right? I don't know how good you guys are at geometry here. So yeah, the thing is like I'm just corresponding sides or something like that, right? So here we have these two sides. We're dividing s over 2 and then the corresponding side is this s plus x divided by 8. Okay, so that's how I got this proportion. And then, well, what would be useful is to actually not have two s's in the equation. I kind of don't like that. So what I'm going to do is I'm going to subtract that one of the s's over. So when I do that, I'm going to have 8 or x over 8 on one side, and I'm going to have a half minus an eighth on the other side. So this is going to be 3/8. S is equal to, well, I could just write this as 1/8x. Okay, so now we have this relationship between s and x. Okay, well, what's helpful then is if we can take the derivative, then we're going to have a relationship between x prime and s prime. And we know x prime, and we're looking for s prime, so then we'll be done. Okay, so we just take that derivative, and this is a derivative with respect to time. So we end up with 3 over 8 s prime is equal to 1 over 8 x prime. Maybe that's why I used d, because I didn't want to have to enunciate so much. We're looking for s prime, so then we get 1/3, and then what's x prime? X prime is 1/2, so we get 1 over 6. And then, of course, we should write units. So in this problem, it's meters per second. Yeah. Okay. So, yeah. Oh, any questions on that? I have to go especially slow today. So, no questions. Okay. Okay. Well, right. Number six, we have an air balloon that is rising, and we have an observer, and we're talking about the angle of the person like viewing the the air balloon. And so what you can imagine is that as the air balloon is going up, the angle which the person has to tilt their head is also increasing. Okay, so we have these two quantities that are changing, and we're told that the observer is 2 miles from the liftoff point. So that gives me this side there. Okay, let's see. So it says at a certain moment, the angle of the line of sight at the horizontal is pi/4. So that tells me that theta is pi/4 for some particular instance in time. Okay, so when theta is equal to pi/4, the angle is changing at a rate of 1/10 radians per minute. Theta prime is equal to 1/10 radians per minute. Okay, so that is the second sentence. And then how fast is the balloon rising at this moment? Okay, so it's saying find h prime. Right. So what I've drawn here is the dynamic picture, the moving picture. And this is specifying for us the static picture. So we can actually go ahead and calculate that. We could draw the static picture right besides it. So in this case, we have an angle which is pi/4, and we know this is 2. Well, pi/4, 45-degree triangle, we know that this is 2, 2, and 2√2. Right? If you don't know that, because this is kind of a special triangle, if you don't know the special triangle, then you could just use Pythagorean formula to calculate the hypotenuse length. But okay. So now at this point, I want to create an equation that's going to hold true for this dynamic picture, this moving picture, some equation that's going to hold true regardless of what point in time I'm looking at the scenario. Okay, so who can tell me what equation I should write down? So figuring out the equation is always the hard part about this type of problem, I would say. Well, maybe all of it is somewhat hard, but this is one of the key parts is actually coming up with that equation. So we want some way of relating h and theta. Can you see a way to relate h and theta to each other? You're going to need a trig formula. That's the hint. Anyone?
Would you use tangent?
Tangent. That's right. That's right. So we have h and we have this 2 over here. So the idea is we figure out like what formula corresponds to the ratio of these two sides. So tangent is the most common one. You could also technically use cotangent, but that's a bit more ugly, more bothersome. So tangent, yeah, opposite over adjacent is tangent. So tangent of theta is equal to h/2. That's the equation that we get. And now, well, what can we do at this point? The only thing we really can do is take a time derivative. So we go ahead and try that out. And then what we expect to get is some formula that's going to relate then theta prime with h prime, which is exactly what we need. We need to figure out h prime, and we're given a bunch of data involving theta and theta prime. We're given specifically theta and theta prime. So with this, we'll be pretty close to being done. So tangent, its derivative is secant squared theta. But then since theta is not t, we have the theta prime, right? This is implicit differentiation. And then right-hand side is 1/2 h prime. Okay. And now I can pretty much plug everything in. The only thing is I do need to figure out what the secant squared theta is. So there's a side calculation that we need to do to figure this out. This is the specific snapshot in time we're dealing with. Okay, so like basically, don't expect to calculate theta. Actually, here we can, yeah, I mean here we can calculate theta, but it's in general you might be given, especially I think, yeah, yeah, in Calc 2 when you start doing like a trig substitution or no trig sub, yeah, trig sub, you have calculations where you can't calculate, where you can't figure out theta, but you can still talk about the triangle that corresponds to the given theta. And so this is kind of the way you should think about it. Instead of figuring out theta, you instead just think about secant as a ratio of sides of, and then you have these ratios here. So you just calculate using that. So cosine is the thing I would start with. I'd start with cosine, then I figure out secant, then I figure out secant squared. Cosine is adjacent over hypotenuse, so we get 1 over square root 2. Secant is a reciprocal, so I get root 2. And then obviously secant squared, I just square it, I get 2. Okay, so now you have 2 times, and now theta prime is given to us, 1 over 10 is equal to 1/2, and h prime is what we're solving for. And then we just go ahead and solve. So 1 over 5, I think. Sorry, 2 over 5. Uh-oh, what did I do wrong? Oh yeah, I can only get rid of one of the 2's. Yeah, it's gonna be 4 over 10, which is 2 over 5. I can't do arithmetic today for some reason. Okay, but yeah, so right, and now we ask ourselves, what are the units for this problem? So this is a height that is changing. So I need a measurement of length and I need a measurement of time. The length measurement here is miles. The time measurement is minutes. So it's a bit unusual, but it's miles per minute in this problem. So there we go. That's the answer for number 6. Any questions? Yeah. So I'm emphasizing units just because I saw a couple of answers where people just wrote down the wrong units. You just like you're so used to meters per second that you don't read that the problem is actually in terms of feet per second. So I had to take a couple points off for things like that. Although I don't think I didn't grade any of my sections, so maybe the other graders aren't as attentive. Anyway, yeah. Conical tank. All right, so a conical tank is always drawn like this. And it looks weird, but the reason is because otherwise you'd have to calculate the volume of a frustum of a cone, which is a bit more bothersome. So yeah, we do it like this just because it's easier. And now the height is 10 feet. The radius is 5 feet. And the water is flowing into the tank at some rate. So water flowing in, that's going to correspond to some volume. So we're going to say that the rate of change of volume is 2 feet cubed per minute. Okay. And we want to know how fast is the water level rising when it is 4 feet. Okay, so in the picture, then I would probably denote this like something like that. We have this with some radius, maybe a bit of a circle there. And this length is going to be my height. Okay, so now that I have all of that, I can write down what this is saying. So how fast is the water level rising? So what is the change in height? Find h prime when h is equal to 4 feet. Okay. So what should come to mind in terms of like the equation that describes the system, you want to calculate right volume of the water. So you have to remember what is the volume of a cone, and it's going to be 1/3 pi r squared h. I don't, well, I mean, I don't remember if the rules say that you're not supposed to be able to look things up online. Can you treat the internet as your notebook? I don't know. But I mean, the way that you normally you'd be asked to memorize basic volume formulas, and the way that this works is a cone is always 1/3 the volume of the cylinder, so that's why you have the 1/3 there. So the rest of this actually corresponds to the volume of the cylinder. And that's actually easy to see because how do you normally calculate volume of a cylinder? You do base times height. The area of the base, which in this case is a circle, it's this circle right here, times the height. Height is there, and then pi r squared is area of a circle. So that's how we know this formula, more or less. The 1/3 is actually the weird thing. Like, how do we know 1/3? You're never actually told that. The answer is actually, as far as I know, the answer is because calculus. You actually the way you derive that 1/3 comes from a derivation in calculus. I don't think there's a geometric way of seeing that, but I could be wrong. But I haven't seen it before. Okay. But anyway, so what I want to say at this point, this formula, normally you would be tempted to just take its derivative right away, take the time derivative right away. And I'm not going to do that here because there's actually more going on to this problem. See, if imagine that you were to take the time derivative here, you would end up with a product rule involving r and h. So you end up having some formula that uses r, h, r prime, and h prime. And then it ends up being a bit more work than actually that you need to, more work than is necessary. The reason is because there is a simplification that you can do. In this situation, there is a dependency between R and H. There's actually a formula that relates the two things. And you can use that to simplify this expression. Okay. So, and this all comes down to similar triangles. So I'm going to draw the flat picture of this. Let's take a look at what we get. So this is R, this is H, uh, this whole thing is 10, and this is 5, right? Just like before in a previous problem, we can set up a ratio of similar triangles. So in this case, I would say R over 5 is equal to H over 10. Okay, so now we have a relationship between R and H. We know that they depend on one another, or one will give you the other. Okay, well, what am I trying to find? I'm trying to find H prime. So that means I want the H to stick around. I want to get rid of the R. I can replace the R if I can write it in terms of H. And so we just move that over. We get H over 2. Okay, great. Now that we know that, we can actually replace out the R here. Okay, so I'm going to end up with 1/3 pi. And then, well, if we square this equation, we get H squared over 4. But there ends up being an extra H there. So I'm just going to combine that together. And I'm going to get H cubed over 4. Okay, so we end up with this equation. This equation, in fact, holds true for all time. And so, like, that's kind of a nice little symmetry, I guess, that the problem inherently has. You can imagine that if the problem was made to be more complicated, like suppose that R and H are somehow forced to not be related to one another. Like imagine that the angle of the cone is also changing with respect to time in some independent way from H. Then yeah, you would actually be forced to do the product rule thing. You'd be forced to use this more complicated calculation. Uh, but here, because they are related, you have this extra equation lying around. You can actually simplify your calculation, and that saves time. That's great. Okay. Now we go ahead and we do the time derivative here. Okay. Now we get v prime, and this is going to cancel. The 3 will cancel with that. So I'm just going to put pi over 4 h squared, and then don't forget the h prime, which is actually the thing we're looking for. Okay, now we can plug, I think, everything in, right? We have v prime, pi over 4, h here. We're in our situation, in our static picture, h is 4, so we have 4 squared times h prime. Okay, and so now we can just calculate what h prime is from this. So we'll get 1 over 2 pi. And then lastly, we tack on the units. So this is in feet per minute. Okay. And so there we go. Any questions? You guys are awfully quiet. Um, well, I don't have anything else to talk about. So if there aren't any questions, then we can end here.
How did you know that ratio of r over 5 equals h over 10?
Mm, so there's two ways to set up ratios. In this case, what I'm doing is I'm ratioing the similar sides, the corresponding sides. So R corresponds to 5, H is going to correspond to 10 in this. Do you see that? The two triangles that I'm comparing?
Yeah, I see that.
Yeah. So that's how I'm using that's how I'm getting this ratio. So R over 5, those are the corresponding sides. H over 10 is the other course set of corresponding sides. There's actually two ways to set up proportions, so that I'm mm, does that answer your question?
Yeah, so that was the same ratio we did for the shadow one, right? So
Uh,
does that also work in like three-dimensional, like I guess it works in
actually,
dimensional
mm,
sense as well?
three. What? For three, you mean like if you have like a cube versus like a scaled up cube, will the corresponding thing still be related?
Yeah, yeah, that's what I'm talking about.
Yeah, that's the way that scaling works, and I think you can be a bit more general too, because it's like if you're talking about things of different dimensions, then the area is gonna have like square in proportion. Like you talk about like a scaling factor. So if your scaling factor is like some number kappa, say, for like a length, then the area is gonna scale by kappa squared, volume will scale by kappa cubed. That's the way that things work in when you vary your dimensions around. But I want to get back to what you mentioned here because actually the thing is that I'm actually doing different proportions for number seven and number five. If you'll note, like what I did here, I'm not my fraction is not set up by taking corresponding sides, not in this problem. It's all because like where are my variables located? I create the proportion that makes sense for my problem. Like I use the one that's more convenient. Here, notice my proportion, I'm doing S over 2. What I did is I divided two sides that are from the same triangle. But on the other side, I'm doing two sides from a different triangle, but I'm doing them in the same order. And that's going to end up giving me a proportion that is still true. All you need to do to go from one setup to another is you switch the two in the diagonal around. And you should know that you can do that because, well, the normal way that you're taught how to solve this thing is you like cross multiply, right? So, of course, you can cross multiply and then you can undo a cross multiply. So you can just swap those two. But there's two different ways to set things up. This is using the other setup. Does that make sense?
Yeah, yeah, that makes sense. So for I guess for like other problems, try to find a ratio kind of similar to what you did. See what I'm saying?
Um, I mean, it really depends on your problem. I'd have to see like what kind of problem you're thinking about. Um, if I mean, yeah, if you suspect, like, if you see anything about similarity, like similar triangles or similar shapes or whatever, then yeah, you're gonna want to set up some kind of proportion like this. Um, but not all things are involving similar triangles, right? Like this thing was not like that at all. Um, it depends on how things vary. Sometimes. But I would have to look at like some more examples of these types of problems. I mean, we do have some time, so if you want to, I can like try to find something more interesting. But uh, it's up to you. Do you want to try to find a more complicated problem? Do you want to give me a complicated problem?
Um, it's probably better if I try to figure it out myself for now, but five
Okay.
questions I'll definitely ask.
Okay. Well, yeah. I mean, and if you're ever really like stuck on something, you can always use the help sessions by other people. I assume that everyone knows about the help session and the calendar. You can find it online. Everyone know about that? It's on Canvas, or it's called Canvas, right? Yeah. Okay. Well, I'm gonna stop recording. Actually, I don't know why.